in your study of physics, you will often encounter the idea of mass, and you will also might encounter the idea of inertia. And what I want to do in this video is think about what is the similarity or the difference between these two concepts or these two ideas in physics. And I'm going to give you a little bit of time to do it. And I encourage you to ask people and search the web and look at textbooks, whatever you can do to figure out the similarities and differences between mass and inertia. So from a historic perspective, if you have asked someone what does mass mean or what does it represent, they'll say it means or it represents how much stuff an object is made up of, or how much matter actually constitutes an object. And if you were to ask them, well, what is inertia then? They'll say, well, inertia is a property of an object. That's really how hard is it to accelerate that object? How hard is it to change that object's velocity? So we could call this maybe resistance to acceleration. So on this first glance right over here, you might say, okay, well, these are two different ideas. And they seem like two different ideas until we start thinking about a couple of things. One, Newton's second law, and also how you would actually go about measuring mass. So how would you actually measure this right over here? How would you measure mass? Because you might say, well, maybe you just look at the size of the object. But the size by itself doesn't tell you how much stuff there is. You could have a very large object that's not very dense, let's say cotton candy or a hot air balloon, and you could have a very small object that's very, very dense. You could take a lead weight or something even denser, a teaspoon of the material from a neutron star, incredibly, incredibly dense, very, very high mass. So you couldn't just look at the size or the volume of an object. But lucky for us, Newton's second law does give us a tool for figuring out the mass of an object. Newton's second law tells us that the force that acts on an object is equal to the mass of that object times the acceleration of that object. And the acceleration and the force are going to go in the exact same direction. Or if you want to think only about the magnitudes, you could say the magnitude of the force on an object is going to be equal to its mass times the magnitude of the acceleration. You say, well, how does this allow me to measure an object's mass? Well, I can apply some force to it. I can apply some force, a certain magnitude, and then I can measure how much that object is accelerated, and then I could just solve for m. You divide both sides of this equation by a, you get F over a is equal to m. But what am I measuring? So I will actually solve for a mass here. I could, I'll get my proper units of mass depending on what my units of force and acceleration are right over here. But what am I implicitly measuring as well? Well, I'm applying a force on something, and I'm seeing how much it's accelerating. I'm seeing what is its resistance to accelerating. So I'm really trying to also determine its inertia. So when you think about mass in this way, we now think about this as actually inertial mass. Inertial mass. One way to think about it is that the mass is actually quantifying that object's inertia. So we can split hairs over the definitions, but in this way of viewing mass and inertia are really the same thing. And it's actually very hard to just directly measure how much stuff or matter there is. That's why I put it in quotes right here. The more pure definition of what mass even is, or one of the more pure definitions of what mass even is how resistant is that object to acceleration. Because especially once you start getting into the subatomic domains, the quantum domains, the idea of how much stuff there is starts to become very abstract, and all we can do is measure how does that entity or that particle, how does that respond to force? How resistant is that to acceleration? And that is essentially what we're describing as mass or inertial mass. But you might say, wait, that's not the only way to measure mass. You have Newton's law of gravitation. I could have some object that has a known mass. So let's say this is some object with a known mass. Let's call it m1. And let's say that there's some other object with an unknown mass. Let's call it m2. And this is the mass that we are trying to measure. And we know that they're going to exert, they're going to pull on each other. Newton's law of gravitation. And everything we're talking here, we're talking about classical mechanics. That's the world we're going to deal with. We're not going to talk general relativity or anything like that right now. But we know, if we know this mass and if we know the distance between them, we know the distance between their center of masses. So just like that. And if we can measure their respective pulls on each other, so we know that if m2 is pulling on m1 with some force, So I'll draw that as a vector like this. M1 will pull on M2 with an equal and opposite force. So a force with the same magnitude, but just the opposite direction. And so we can measure what that force is. We know what M1 is. We know the distance between them. And from that, we can figure out what M2 needs to be. And when you measure mass, or when you think about mass in this way, you're actually referring to gravitational mass. Let me write it this way. This right over here is gravitational mass. Now, lucky for us, it has been verified that these two things are actually measuring the exact same thing. That inertial mass is equivalent to gravitational mass. So you can debate on the definitions, and it might be a little different in different contexts. Sometimes people want you to think of it more in classical terms. Inertia is resistance to acceleration. Mass is how much matter there is. But essentially, they're talking about the same thing. Mass is a measure of how resistant something is to acceleration, or mass is a measure of inertia.